dual illumination on this
Out
world
there
is
in the
one
silent,
striking.
star-dusted theatre of the cosmos, a familiar scene plays out an infinite number of times. A solitary star, a pinpoint of fusion-forged light, holds a family of worlds in its unwavering gravitational embrace. This is the architecture. We know the blueprint of our own home. But the universe is not a creature of habit. Its imagination is wilder, its engineering more audacious than we dare to conceive. Imagine standing on the surface of an alien world where the ground beneath your feet is bathed in the light of not one but two suns. The sky is a canvas of impossible colors. One star, a fiery ruby, hangs low on the horizon while its companion, a smoldering orange ember, climbs toward the zenith. They cast twin shadows from every rock, every mountain, every living thing. Shadows that stretch and shrink that dance and intertwine a silent, ghostly ballet dictated by the complex orbits of two stellar masters. This is not a flight of fancy from a storyteller's dream. This is a reality, a tangible place, catalogued and scrutinized by our finest instruments. For decades, we called these circumbinary planets worlds orbiting two stars, Tatooine-like, a nod to a fiction that captured our collective imagination. We have since found that reality is far stranger and far more profound. Our unblinking eye in the void, the transiting exoplanet survey satellite, ceaselessly scans the celestial sphere for the faintest whispers of other worlds. It looks for the telltale dimming of a distant star, the momentary shadow cast by a planet crossing its face. And in a faint constellation it found something that defies our understanding. It found a system designated TOI-2267. A place where two red dwarf stars are locked in a furious, intimate dance, whipping around each other in a gravitational vortex of staggering power. And, orbiting this chaotic, violent heart, not one but three planets, a trio of worlds that, according to everything we thought we knew, should not exist. This is the story of that impossible system. It is a tale of cosmic architecture on the grandest scale, a mystery that challenges the very foundations of how worlds are born. TOI-2267 is not just a discovery, it is a declaration from the universe itself that its capacity for creation is vaster than our theories have yet allowed. The human mind has long been captivated by the notion of plural suns. Ancient mythologies from every corner of our own world speak of celestial beings, of gods and spirits who populated the heavens. They wove tales of cosmic battles and celestial marriages, filling the sky with characters as complex as those who walked the earth. But it was in the nascent flicker of science fiction that the idea of a world with two suns truly took root in our culture. It became a powerful visual shorthand for the alien, the exotic, the truly other. A desert planet, its twin suns beating down on endless dunes, became an iconic image, a symbol of a galaxy far, far away. This vision, Tatooine, painted our dreams of what might lie beyond. It suggested that the neat, orderly model of our own solar system was perhaps just one of many possible arrangements. The concept was so potent, so visually arresting, that it prepared our minds for the strange realities astronomy would later unveil. For centuries, astronomers who gazed at the firmament noted that many stars appeared not as single points of light, but as close pairs. The prevailing assumption for a long time was that these were mere line-of-sight coincidences, two unrelated stars at vastly different distances that just happened to align from our terrestrial vantage point. It was a sensible, conservative assumption. The alternative was almost too radical to contemplate. The idea that two suns could be gravitationally tethered, locked in a perpetual waltz through space-time, was a profound leap. It transformed the sky from a static tapestry into a dynamic, interactive arena. The great observer William Herschel, in the late 18th and early 19th centuries, dedicated years to meticulously tracking these stellar pairs. With painstaking patience, he measured their positions night after night, year after year. He discovered that they were not stationary relative to one another. They were moving, tracing out slow, graceful arcs around a common center of gravity. This was irrefutable proof. Binary stars were real. They were not optical illusions, but physical systems of immense scale and power. The galaxy, it turned out, was filled with them. In fact, we now know that systems with 2 or more stars are not the exception. They might well be the galactic norm. This revelation opened a Pandora's box of cosmological questions. If 2 stars could orbit each other, could planets orbit them? The initial scientific consensus was a resounding no. The gravitational environment around a close binary pair was thought to be a planetary death trap. It would be a zone of utter chaos, a cosmic blender. Imagine the birth of a solar system. It begins as a vast, placid cloud of gas and dust. Gravity slowly coaxes this material into a spinning disk, a protoplanetary nebula. Within this disk, tiny dust grains frosted with ice gently collide and stick together. It is a process of delicate incremental construction. A single stable star at the center of this disk provides a steady gravitational anchor, but introduce a second star, especially one in a close, fast orbit. The gravitational field becomes a maelstrom. The 2 stars would act like immense rotating beaters in a cosmic mixing bowl, stirring the nascent disk into a frenzy. The gentle collisions required for planet formation would become violent impacts. Instead of building up dust grains and pebbles, would shatter each other into oblivion. The binary's gravitational influence would also carve out a vast empty region at the very heart of the disk, ejecting the raw materials for planet building into the cold, dark extremities of the system, or out into interstellar space, entirely. For decades, the idea of circumbinary worlds remained in the realm of fiction. Our models were clear: such places were forbidden zones for planetary formation. The universe, however, was patiently waiting to prove us wrong. It required a new generation of sentinels, new ways of seeing, to pull back the curtain on these seemingly impossible creations. Finding a world hundreds or thousands of light years away is one of the most sublime technical challenges humanity has ever undertaken. An exoplanet is cosmically small, emits no light of its own, and is hopelessly lost in the overwhelming glare of its parent star. It's like trying to spot a firefly sitting on the beacon of a lighthouse from across an ocean. To overcome this, astronomers devised a beautifully simple yet powerful technique, the transit method. The logic is straightforward. If a planet's orbit happens to be perfectly aligned with our line of sight, it will periodically pass directly in front of its star. When this transit occurs, the planet blocks a tiny fraction of the starlight. This causes a minuscule temporary and repeating dip in the star's brightness. The challenge is that this dip is astonishingly small. For an Earth-sized planet crossing a Sun-like star, the brightness drops by less than 1 part in 10,000. To appreciate the sensitivity required, let us construct an analogy. Picture yourself on a ship in the dead of night, sailing a vast dark sea. Far on the horizon, a single brilliant lighthouse pierces the blackness. Your mission is to measure the constancy of its beam. You have a light meter of exquisite precision. Now imagine that a single tiny gnat is flying around that distant lighthouse. Most of the time its flight is invisible to you, but every so often, purely by chance, its path takes it directly across the lighthouse lens. For a fleeting moment, the gnat's body obstructs an infinitesimal portion of the light. From your ship miles away, your detector would register a flicker, a dip, so subtle it's almost imperceptible. That is the work of our planet-hunting telescopes, like Kepler and its successor TESS. They are the sailors on the cosmic ocean. The stars are the lighthouses. The planets are the gnats. These observatories stare unblinking at hundreds of thousands of stars, simultaneously measuring their brightness with a cadence and precision that borders on the miraculous. They are hunting for those fleeting rhythmic flickers amidst a storm of cosmic noise. The TESS satellite, the Transiting Exoplanet Survey satellite, was designed to conduct an all-sky survey, a grand census of our stellar neighborhood. Its 4 powerful cameras divide the sky into sectors, staring at each patch for nearly a month before moving on to the next. It generates a deluge of data, a torrent of light curves from distant suns. This flood of information is so immense that professional astronomers alone cannot sift through it all. And so a new era of discovery was born, one powered by collective curiosity. Projects like Planet Hunters TESS invite citizen scientists, volunteers from all walks of life to look at the same data, to lend their pattern recognition skills to the search. It was one of these volunteers who first flagged something unusual in the light curve of a faint star, a star that would come to be known as TOI-2267. The data showed not just one dip, but a complex series of dips with irregular timing and varying depths. It was not the clean, simple signature of a single planet around a single star. This was something different, something complicated. The signal was messy, chaotic, and tantalizing. It was the first breadcrumb on a trail leading to a system that would strain our theories of celestial mechanics to their breaking point. The professional astronomers took over, pointing ground-based telescopes toward the target. They needed to confirm the nature of the star system itself. Using techniques like spectroscopy, they split the starlight into its constituent colors, a rainbow barcode that contains a wealth of information. This stellar spectrum revealed the telltale signs of not one but 2 stars. The spectral lines were doubled, and they were shifting back and forth in a rhythmic pattern. This is the Doppler effect in action. As the 2 stars orbited each other, one would be moving toward Earth. Its light blue shifted to higher frequencies. Simultaneously, its companion would be moving away. Its light red shifted to lower frequencies. The speed and period of this spectral dance told a remarkable story. The 2 suns of TOI-2267 are M dwarfs. They are smaller, cooler, and far dimmer than our own Sunday. They glow with a ruddy, cherry-red light like cosmic embers. But what is truly astonishing is their proximity. They are locked in an orbital embrace, so tight they complete a full revolution around each other in just 7.3 days. This is the heart of the enigma. They are a contact binary, 2 suns spinning in a gravitational whirlpool. To comprehend the violence of this environment, let us refine our earlier analogy. Imagine not just a mixing bowl, but 2 massive bowling balls tethered by an incredibly short, powerful steel cable. Now spin these tethered bowling balls on the surface of a giant taut trampoline. They whirl around a common center at a dizzying speed, warping the fabric of the trampoline around them in complex oscillating patterns. This warped fabric represents the gravitational field. It is a landscape of extreme peaks and plunging valleys, all of them moving, all of them changing. Now attempt to form planets in this environment. Sprinkle fine dust onto this wildly spinning, wobbling trampoline. The dust would not be able to gently clump together. It would be flung around, violently accelerated to high speeds by the shifting gravitational gradients. Any small collections of dust would be ripped apart by tidal forces or ejected from the system entirely. Yet somehow, against all odds, the universe built planets here. The TESS data, confirmed by extensive follow-up observations, revealed the unmistakable signatures of 3 distinct worlds. These are not small rocky bodies. They are substantial planets classified as sub-Neptunes. They are TOI-2267 B, C, and D, worlds larger than Earth but smaller than our own ice giants. They likely possess thick, dense atmospheres cloaking a solid or liquid core, and most critically, their orbits are circumbinary. They do not orbit one star or the other. They orbit the spinning binary center of mass of both. Planet B, the innermost, completes its journey around the twin suns in just under 27 days. Planet C takes about 45 days, and the outermost world D has an orbital period of roughly 64 days. They are huddled remarkably close to the chaotic central engine of their system. They exist in what should be the most hostile, unstable region imaginable. The survival of this trio points to a hidden order amidst the chaos. Their orbital periods are not random. They exhibit a near resonance, a delicate gravitational relationship that keeps them stable. For every few orbits, the inner planet the middle one makes a set number, and the outer one completes a corresponding whole number of its own. Think of it as a form of celestial music, a cosmic harmony. Imagine 3 pendulums of different lengths, all swinging from the same support. If you set them in motion randomly, their swings will be chaotic and unsynchronized. But if you tune their lengths just right, they can fall into a resonant pattern, swinging back and forth in a beautiful, repeating, stable dance. This orbital resonance is the only thing preventing the 3 planets of TOI-2267 from gravitationally interfering with one another and tearing their own system apart. It is a testament to an unseen hand of physics, a self-correcting mechanism that brings order to the brink of catastrophe. But this stability only deepens the central mystery. How did they get here? The existence of this tightly packed, resonant trio of planets presents planetary scientists with a profound crisis. It is a direct assault on the standard, cherished model of planet formation. That model, known as the core accretion theory, has served us well for decades. It elegantly explains the architecture of our own solar system and many others. It begins with the aforementioned protoplanetary disk, a vast spinning pancake of gas and dust surrounding a newborn star. Within this disk, microscopic dust grains, through electrostatic forces, begin to stick together, forming larger and larger aggregates. Over millions of years, these grow from fluffy dust bunnies into pebbles, then boulders. These larger bodies, now called planetesimals, begin to exert a meaningful gravitational pull. They sweep up more material in their orbital path, growing ever larger. Eventually, a few dominant bodies emerge, planetary embryos the size of our Moon or Mars. This is the core-in-core accretion. Once this core reaches a critical mass, its gravity is strong enough to rapidly pull in a thick atmosphere of gas from the surrounding disk. This is a slow, methodical, almost gentle process of construction. It requires a stable environment, a steady supply of raw materials, and millions of years of relative tranquility. TOI-2267 offers none of these things. Let us revisit the scene of the crime, the protoplanetary disk around the nascent binary stars. The first major problem, the one we have touched upon, is the sheer gravitational disruption. The 2 stars whipping around each other every week would send powerful gravitational waves pulsing through the disk. These ripples would pump energy into the orbits of all the dust and pebbles. Their relative velocities would increase dramatically. Instead of gentle, constructive collisions, you would have high-speed, destructive impacts. Pebbles would not stick. They would shatter, grinding each other down into smaller and smaller dust. The process of accretion would be stopped dead in its tracks before it could even begin. It's like trying to build a delicate sandcastle in the middle of a continuous earthquake. The very ground upon which you build is conspiring against you. The second, perhaps even more insurmountable problem is one of material starvation. The gravitational dance of the binary stars doesn't just stir the disk, it clears it out. Through a process called dynamical clearing, the binary's influence creates a large central cavity in the protoplanetary disk. It acts like a cosmic snowplow, pushing all the gas and dust away from the central region. Calculations show that for a binary as tight as TOI-2267, this cleared-out cavity would extend far beyond the current orbits of all three known planets. In other words, the planets are located today in a place where there should have been virtually no raw material to build them in the first place. They are houses built in the middle of a barren desert with no sign of a quarry for miles. The standard model simply collapses under the weight of these contradictions, so scientists are forced to venture into more exotic speculative territory. If the planets could not have formed where they are now, perhaps they were born somewhere else and moved. This is the theory of planetary migration. Under this scenario, the three worlds of TOI-2267 formed much farther out in the protoplanetary disk. Out in these colder, more distant regions, the gravitational influence of the central binary would have been far weaker. The environment would have been calm enough to allow the slow, steady process of core accretion to proceed. 3 sub-Neptune worlds could have been built in peace, but then something must have prompted them to journey inward. The leading mechanism for this is interaction with the gas disk itself. As a massive planet plows through the gas, it creates spiral density waves, much like the wake of a ship moving through water. These waves in turn exert a gravitational drag on the planet, causing it to lose orbital energy and spiral inward toward the stars. The 3 planets would have migrated together, a slow procession toward the chaotic center. As they moved inward, their orbits would have shrunk and they would have eventually been captured into the stable resonance we observe today. This resonance would have acted as a brake, a stabilizing force that halted their inward march before they plunged into one of the 2 suns. This migration hypothesis is plausible, and it solves the problem of the barren inner disk. However, it presents its own set of challenges. The process of migration is notoriously difficult to stop. What precise mechanism put the brakes on at just the right moment? Getting 3 planets to migrate together and lock into such a specific resonance is a feat of exquisite fine-tuning. This leads us to a more radical alternative disk instability. This model abandons the slow, gentle buildup of core accretion entirely. It posits that under certain conditions, if a protoplanetary disk is massive and cold enough, it can become gravitationally unstable. Large portions of the disk can collapse directly under their own self-gravity, bypassing the intermediate steps of pebble and planetesimal formation. It is a violent, chaotic, and incredibly rapid method of planet building. Instead of taking millions of years, giant planets could form in just a few thousand. This speed might be the key. Perhaps the planets of TOI-2267 formed in a massive, unstable disk before the central binary had enough time to fully clear out the inner cavity. They would have sprung into existence almost fully formed from collapsing clumps of gas and dust. This model avoids the problem of high-speed collisions preventing accretion because it skips that step altogether. However, the disk instability model has typically been used to explain the formation of giant Jupiter-like planets in the outer reaches of a system. Whether it can form smaller sub-Neptune-sized worlds so close to their host stars remains a topic of intense debate. TOI-2267 forces us to push these models into uncharted territory. The very existence of this system is a testament to the universe's versatility. It tells us that where there is a will, or at least a sufficient amount of matter and gravity, there is a way. The processes that build worlds are more robust, more varied, and can operate under far more extreme conditions than we ever dreamed. Let us now leave the realm of theory and data of light curves and spectral lines. Let us travel across the light years and stand on the surface of a hypothetical moon orbiting one of these impossible worlds, perhaps the outermost planet TOI-2267d. What would we see? What would we feel? The experience would be utterly alien, a symphony of light and motion. The sky above would be a stage for a relentless celestial drama. The two suns our red M dwarfs would trace complex looping paths across the heavens. Sometimes they would appear close together, a dazzling, fiery pair. At other times they would be on opposite sides of the sky, bathing the landscape in a cross-fading dual-source light. There would be no simple sunrise, no singular sunset. Instead, there would be periods of double dawn as the two stars rise in succession, one chasing the other over the horizon. And there would be twin dusks, with one sun setting while the other still hangs high in the sky, prolonging the day in a wash of ruddy dimming light. True night, the profound blackness we know, might be a rare event. It would only occur during periods when the planet's location in its orbit places both suns behind the planet's body at the same time. For much of the year, the sky would be in a perpetual state of twilight, one star rising as its companion sets. The light itself would be different. Red dwarf stars emit most of their energy in the infrared part of the spectrum. To our eyes, the illumination would be a deep, permanent, coppery glow. Plant life, if it were to evolve here, would need to adapt to this lower energy red-shifted light. Photosynthesis would operate under entirely different rules, perhaps resulting in vegetation with foliage of black or deep purple to absorb as much energy as possible. And then there are the shadows. On Earth, we are accustomed to a single shadow, a simple projection of ourselves. On this world, you would almost always cast two distinct shadows, one perhaps sharper and darker, the other softer and more diffuse, depending on the relative positions and brightness of the two suns. These shadows would move constantly, lengthening, shortening, and sweeping across the ground in a disorienting, hypnotic dance driven by the binary's 7-day whirl. Life evolving here would face unique challenges and opportunities. Circadian rhythms, the internal clocks that govern sleep and wakefulness, would need to attune themselves not to a simple day-night cycle, but to the complex multi-period rhythm of the two suns. The concept of a day would be ambiguous, a fluid definition in a world of overlapping light. The system's habitable zone, the narrow band of orbits where liquid water could exist on a planet's surface, would also be a dynamic, shifting entity. As the two stars orbit each other, their combined energy output in any given direction fluctuates. The habitable zone would wobble and warp, expanding and contracting with each 7-day period. For a planet to remain life-sustaining, it would need a thick, insulating atmosphere to buffer against these rapid temperature swings. The discovery of TOI-2267 does more than just present a fascinating puzzle. It fundamentally reshapes our perspective on the cosmos and our search for life within it. For a long time, planetary searches tended to avoid binary star systems. They were considered too complex, too chaotic, too unlikely to harbor stable planets. They were filtered out of search algorithms as poor candidates. This system and others like it have proven that assumption to be a colossal mistake. Binary and multiple star systems are not galactic curiosities. They are a dominant mode of stellar existence. Roughly half, if not more, of all the Sun, like stars in the Milky Way, are part of a multiple system. By demonstrating that stable multi-planet systems can form even around tight binaries, TOI-2267 effectively doubles the number of potential homes for life in our galaxy. It throws open the gates to a vast, previously unexplored cosmic real estate. Our search for habitable worlds can now expand with newfound confidence into these complex and dynamic environments. The universe is not limited to the simple, single-star architecture of our own solar system. It is a far more diverse and creative place. The next generation of astronomical tools will bring this impossible system into sharper focus. The James Webb Space Telescope, with its unparalleled infrared sensitivity, is perfectly suited to study worlds orbiting cool red M-dwarf stars. While these planets are too distant for JWST to image directly, it may be able to analyze their atmospheres. As one of the planets transits its host stars, a sliver of starlight will pass through its atmosphere on its way to the telescope's mirror. Imprinted on that light will be the chemical fingerprints of the gases present. JWST could search for the signatures of water vapor, methane, or carbon dioxide. Such a detection would transform these worlds from statistical data points into tangible places with skies, weather, and the potential for chemistry we understand. TOI-2267 is a profound lesson in cosmic humility. It reminds us that our theories are just that models' approximations of a reality that is consistently grander and more surprising than we predict. Each time we think we have understood the rules of the game, the universe deals us a hand that forces us to rethink everything. We once believed the Earth was the center of all things. We once believed our solar system was the only one. We once believed that planets could only form around single well-behaved stars. Each of these assumptions has been shattered, replaced by a more expansive and magnificent truth. The universe is not hostile to the formation of worlds. It seems to relish it, conjuring them into existence in the most unlikely and spectacular of settings. The 3 planets of TOI-2267 are silent witnesses to a violent and mysterious creation. They orbit their twin suns in a quiet, stable harmony, their existence a paradox that will fuel scientific inquiry for decades to come. They are a beacon reminding us that there are more things in heaven and earth than are dreamt of in our philosophies or contained within our equations. Out there in the endless sea of suns, countless other impossible worlds await their discovery. The search, fueled by wonder and guided by the faint light of distant stars, continues.